So in the 2018 free response and in the 2017 MC of AP Physics C Mechanics, they have addressed the issue that when you have an object approaching another, so the free response actually had a cart with a spring on it and another one was coming in at it. In the multiple choice, they don't tell you what it is. They just gave you U as a function of position, R, but told you that basically you knew that it was a repulsive force, and so it was the same idea, whereas this one came in. For that one, they don't even make contact. When this one came in, the other one starts to take off. And both of them use this idea that at closest approach, that their velocity must equal the velocity of the center of mass. And conceptually it makes sense, right? Because one, in both cases, one was at rest, and then let's see, VI, let's call this B, this will be A, right, was traveling. So it makes sense conceptually, because what you see is this one was going fast and basically overtaking it, and then this is going to get slowed down in the free response by the spring, in the multiple choice by that repulsive force. This one's slowing down while this one's taking off. And so you can just conceptualize why that must be true, because basically, as this one's going to get slower and slower and this one's going to get faster and faster, the point where they'll cross is the velocity of the center of mass. But what I'm going to do right now is I'm going to mathematically show you why it is correct. So not just arguing it conceptually, but why it's correct. So if they're at closest, that means the displacement of object, A minus the displacement of object B is smallest. It's going to be a minimum. So we know from calculus, when we figure out minimums, we take the derivative and we set it equal to 0. So I want this to be minimum, so I'm going to take the derivative of both sides. So I'm going to take the derivative of the displacement of A with respect to time, and I'm going to take the derivative of the displacement of B with respect to time, and I'm going to set that equal to 0 to find that minimum. And I see, well, the derivative of position is velocity minus the velocity of B, and that equals 0, which means that the velocity of A equals the velocity of B. So that right there tells you that at closest approach, they have to have the same speed. So you might say, well, yeah, but how do I know it's the center of mass speed? So they have to be the same speed. And again, hopefully conceptually that makes sense. One's coming in and slowing down, the other one's going to take off. And so when they have that same speed is when they're closest, and beyond that the other one's getting even slower and the other one's getting even faster, so the separation is going to be greater and greater. And before that point, the one was overtaking the first one. So again, hopefully conceptually it makes sense that that they have the same speed at closest approach. How do I know it's the center of mass? Well, if I just use conservation of momentum, initial equals final, then initially I would have, MAVAI plus MBVBI. Afterwards, when they're at closest approach, I know they have the same speed. Again, I haven't proven yet that it's the center of mass speed, but I know they have the same speed. So that means this would be MAV, I'm going to call it, closest approach, equals plus MB V, and that's the same V, so V of closest approach. And so this right here we know is just in general the sum of all momentum, and then I can factor out V of closest approach, so I would have MA plus MB times V of closest approach. But we also know that the net momentum is equal to the total mass times the velocity of the center of mass. And the total mass is ma plus mb. So that means that the velocity of the closest approach is equal to the velocity of the center of mass. And there you go.